and then hex back to decimal and also back to binary. Okay, and today we're going to continue on how to convert, all right, on how to do the addition and subtraction. Okay, so for example, we have A and B, so which are the binary digit. Okay, so let's say we have A plus B and we have 0 plus 0, so we have two slots, one for carry and then another one for sum. Okay, so the carry is the one that is carried out from the sum. Okay, so let's say A plus B, the sum with 0, so there will be no carry, so the carry will be 0. Okay, so if A plus B, either of them is 1, so of course the sum will be 1. But as I said, because it are binary, so the maximum sum can be is only 1, so it's between 0 and 1. So other than that, it must be bring forward to the carry. So for example, for the last one, so when 1 plus 1, which is 2, all right, so the carry must be 1 and the sum must be 0. So it is like the sum is 2 to, all right, it's from 2 to 0, okay, and then 2 to 1. So when 2 to 0 is 0 and then 2 to 1 is 1, so of course the answer is 2. Okay, so let's note here. So it is like here it's 2 to 0, okay, and here is 2 to 1. Okay, so when 2 to 1 is 1, so of course this will be equivalent to 2. Okay, and then when 2 to 0 is 0, of course it's 0. Okay, and then when 2 to 0 is 1, it will be 1, and also 1, and of course 1 times 0 will be 0. Okay, I hope that's you are clear with that. All right, and then we have another example. So we want to add the binary numbers. We need to check against its decimal equivalence. All right, so whether it is similar or not, so we just sum up. So this is the way we sum up the binary number. Let's say over here we have the binary. Okay, 1 plus 1, it will be 2, right? So it will be 1, 0. Okay, so you carry forward 1 to the second digit. All right, so it will be 1 plus 0, so it will be 1. So that is okay. And then 1 plus 0 will be 1, and then 1 plus 1, it will be 2. All right, but 2 in terms of binary, it will be 1, 0. So that's why you get this answer. Or you can even do the conversion first to the decimal. Do the conversion to the decimal, and then you add that, so you get 22, and then convert back to binary. That can also be done. Okay, so 1101 equal to 13, and this one equals to 9, so you just add both of that. All right, so you got 22, and then you can convert back to the binary, so you get 10110. Okay, all right, so all computers use the addition process to implement subtraction. Okay, computers have adder circuitry, okay, but no separate circuitry for subtractors. Okay, as you remember, when you learn in the electronics, remember that we have the adder, all right, but you notice that there was no subtractor, right? So you just have adder, but how you want to implement the subtraction? Okay, so adders are used in conjunction with 2's complement circuitry to perform subtraction. So we still use the adder to perform the subtraction. So to implement x minus y, okay, the computer take the 2's in complement of y and x equal to x. Okay, we will look for the example. Okay, so to get the 2's complement of a binary number, so first we need to invert all the bits and then add 1 to the result. Okay, for example here, we take 2's complement of 1 0 0 1 1 1. Okay, you look over here. Okay, as is said here, so we need to invert all the bits. Okay, we need to invert all the bits and then add 1 to the result. So how to do that? So all right, there's something missing here. The number here, all right, the number here should be like this. Okay, so the number should be 100 111 01. Okay, so this is the binary number. Okay, first we invert all the bit. So invert means, okay, 1 becomes 0, 0 becomes 1, okay, and so on. 1 0 1 0 1 0 0 to 1 0 to 1 and 1 to 0. Okay, once you invert that, so this is the inversion. Once you do the inversion and then you add 1. Okay, so it becomes the 2's complement. The 2's complement. So where the result will be 0 1 1 0 0 0 1 1. Okay, all right, so inverting the bits, this step, okay, inverting the bits is simply the method of changing, as I just said, from zeros to 1 and 1 to zeros. So this is called, inverting the bit is called 1's complement. Okay, okay, so to add, we start the list infinity and add the digits together. Okay, so if the results, okay, less than 64, this one is for the hex numbers. Okay, but this one is for the binary number. Okay, we go to the hex addition, all right, and subtraction. Let's see. Okay, if the result is less than 16, the write that digit as the sum for that position. Okay, if greater than 16, subtract 16 from it to get the digit and carry 1 to the next digit. So for example, so we have 23 D9 plus 94 DE. Okay, so we add. Okay, so to make it simple, right? To make it simple, we need to know what is E in terms of decimal. So we need to know this is in terms of decimal. So in terms of decimal, what it is? Okay, because we only have F. As remember that it's from 0 to 15, right? From 0 to F. Okay, so you have E. So E should be 14. So 9 plus 14, it should be 23. So you take this 23, okay, and then you need to, because 23 is bigger than 16, so 23 is bigger than 16, because you want to put the carry bit on the second digit, okay? So you must convert that to the base 16 first. So what it is, the digit? So the digit is 7, because you need to subtract 16 from this 23. So you got 7, all right, with a carry. Okay, So carry, meaning that you add 1. So carry, you add 1 there. And then, so as like the first one, so you also add D with B. So how much is D? So D, okay, is 13. Alright, D is 13 and B is 11. So you add with the carry 1, so you get 25. Again, 25 is bigger than 16. Alright, so you left with 9, alright? And then you have a carry. So you add another one here. Okay. Then you add 3 and 4, you got 7 plus 1, it should be 8. So 8 is less than 16, so you don't need to subtract with 16. So you just put 8 and there is no carry. Alright, and then you add 9 with 2, so it should be 11, and 11 in terms of hex is B. Okay, so that's how you get this answer. Alright, so that's how you do the addition for the hex. Okay, now if you want to do the subtraction, okay, if the second digit is greater than the first, okay, then you need to borrow 16 from the preceding digit. Okay. Okay, so over here, I think this example is not correct. Okay, this is for the addition. Okay, no problem. I will show you later on how to perform the subtraction of 2 hex digit. Okay, let's continue with the numbering and coding system for ASCII code. Okay, so because all information in the computer must be represented by 0 and 1, the binary pattern must be assigned to letters and other characters. Okay, so how do we get the name of ASCII? So the name of ASCII is found in the 1960 as a standard representation, okay, based on the name of American Standard Code for information interchange. Okay, so as I pronounce, it's pronounced as SE, okay, ASCII. Okay, so it assigns the binary pattern for numbers 0 to 9, okay, and all English alphabet, okay, upper and lower case. All right, so that's what you have in your keyboard right now, okay. So that is in the ASCII representation. So it will be hard for you if the keyboard is just in terms of binary 0 and 1. So how you want to convert that? So to make it user friendly, that's why the ASCII was established. Okay, so that's why the binary patterns must be assigned to letters and other characters. Okay, so all right, so the ASCII code is used by most computers, so information can be shared among them, right? So the ASCII uses a total of 7 bits to represent each code. Okay, so all right, for example, you have on the right, okay, so you have the hex. Okay, in terms of hex, you have 41. Okay, but 41 is considered as A. Okay, B as 42, C 43, D, and so on. Okay, so it starts from 41. Okay, so often a 0 is placed in the most significant bit position to make it an 8-bit code. Okay, so as said here, the ASCII uses a total of 7 bits to represent each code. Okay, each code here is represented by the total number of 7 bits. Okay, so a complete list of ASCII code, okay, you can check in this book in the appendix F. All right, so the hex started from 41 and above. All right, 41 until 60. Okay, 41 until 60. And then for the smaller letter, all right, so it starts from 61. Okay, it starts from 61 until 80. So it should be from 41 to 70 to represent all of the alphabet. Okay, so lower than that, so you might be guessing what is used lower than that, right? So it might be some of other symbols, right? So it's not the alphabet. So the ASCII is standard for keyboards and provides a standard for printing and displaying characters by the output devices. Okay, the pattern of ASCII was designed to allow for easy manipulation of the ASCII data. Okay. All right. So as you can see over here, so digits 0 to 9, as I just said, is represented by ASCII codes from 30 to 39. Okay, for alphabet, it starts from 41 to 70. Sorry, here it should be 80. 41 to 80. All right. And for digits 0 to 9, it is represented by 30 to 39. Okay. So this enables a program to convert ASCII to decimal by masking off, changing to 0, okay, the trees in the upper nibble. Okay. All right. So so when it is 0, okay, so here as the digit, okay, now the computer will learn. All right. So when you are coding, okay, when you press 0 on your keyboard, so it will instruct computer to read code number 30. Okay, so it codes number 30. So this is what is meant by we need to convert ASCII to decimal by masking off, okay, changing the 0 in the tree, okay, this tree, okay, in its upper nibble. So this upper of this one, right? So the conversion between the uppercase and lowercase is as simple as changing the bit 5 of the ASCII code. Okay, this is the example of the other codes used, right? The other codes used for the ASCII. Okay, so you know this is for the alphabet. Okay, starting from 41 until 80. Okay, until 80. And then for other than that, so these are used for symbol from 0 until 29. It's used for symbol. For 30 until 39 is used for digit, the number. Okay, and then between 40, all right, it's not called 40, all right, because the 40 is used as this one. So it's 3A, 3B, 3C, 3D, 3D, E, and F. Because this one, okay, This one is used for symbols, other symbol. Because why? Because the people want to make it easy. So you can just remember that when you're using 3 and these are the digits, okay? So this already represent the real digit on the keyboard, okay? And then for this one, okay, as you look over here, it is easy to just use the alphabet, okay, the capital alphabet in terms of digit as well, from 41 until 5A, okay? And then you look at the pattern. So between 5B to 5F, okay, to fill in between the capital with the small letter, so they put the symbol, okay? So that's how actually it is arranged, okay? Okay, so that's why they use that, right? They use this one, okay, the number to represent the digit and also for the alphabet, okay? And then you can see again at 3, 4, 5, and 6 and 7. So from 3 to 7, that is all used for digits and also alphabet. Other than that, it is used for the symbols. Okay, so the signal in digital electronics have two distinct voltage level. All right, so a system may define 0 as logic 0 and plus 5 volt as logic 1. Okay, because you know that the computer operates only for the binary digit. Okay, but how you start the computer? You start the computer by using the electrical signal, right? So you need to inject the voltage. You need to inject the voltage to the motherboard of the computer, and then how the computer we need to convert. All right, we need to convert that electrical signal into the digital signal. All right, because the computer only works with the digital signal. Okay, so whenever the voltage is 0, so that becomes logic 0. Okay, when the voltage is at 5 volt, okay, so that is considered as logic 1. But it may be ranged around 3 to 5, as you can see in the picture. So it may range between 3 to 5. When the computer detects the voltage is between that range, then it is considered that as a logic 1. Okay, so all right, so this shows actually the tolerance. Okay, let's say the voltage is 3.7, it is still considered as the logic 1. But if it is below 3, then it won't instruct any logic, okay, until 1. Okay, so in this area, it won't instruct any logic. So that means if the voltage is between that, meaning that there is some error within the circuitry of the computer. Okay, so the binary logic gates are a simple circuit. So now we are entering the logic gate. So this is actually what also you learn in the electronics. Okay, so why we need to have these logic gates? All right, because the computer, as it names, is doing the computation. The computation is also equals to calculation. So that's why you need to have this gate. This gate is considered you add these two numbers and then you add what's the result. Maybe you want to do the subtraction and then you get what kind of result. Maybe you want to do the multiplication and then you get what kind of result. Maybe you want to do the division and you get what kind of result. Okay, so that's the function of the logic gate. So the logic gates take two or more inputs to perform the logic operation. Okay. So let's say over here we have the AND gate. All right. So the AND is considered, let's say, we are the comparing two signal input. If both are similar and then both are similar at 1, then it's only turn on. Then you give the output of 1. So that's the function of AND gate. Okay, so the AND gate means that you multiply both of X and Y. Okay, so you multiply these two, 0 and 0, you got 0, 0 and 1, you got 0, 1, 0, you got 0 and 1, and 1, you got 1. So that's the function of AND gate. To turn on when both input are on. All right, so for OR gate, it will be either one of the input is turned on. So as long as one of the input or both input are on, then you can turn on. All right. So as you can see from this table, okay. So either you have X or Y is on, is 1, then the result will be 1. Okay. So you also have the buffer. Okay. So over here, let's say we have a tri-state buffer. So the function of a buffer, it does not change the logic level of the input. Okay, it is used to isolate or to amplify the signal. So this is the symbol of a buffer. Okay, so let's say X going to Y, or it won't change the logic. Okay, but maybe from X we have 3 volt, and then Y, when we go to the buffer, it is increased up to 5 volt. So that is the function of the buffer. Okay. All right. So we also have inverter. Okay. Invert meaning that it change the input. All right. So if X is 1, then the result, the output will be 0. If X is 0, then the result will be 1. Okay. As you can see, the symbol of inverter is almost similar to buffer, except that the buffer does not have this circle, the small circle over here. So that's why when you put 1 over here, the result will also be 1, except that the signal might be increased. Okay. All right. You also have the XOR gate. So X stands for exclusive OR gate. So as before, the operation of OR is to turn on when any of the input is on. All right, when any of the input is 1, so you get the output as 1. Right, but exclusive, because for OR, when both X and Y, the both inputs are 1, the result will also be 1. But for the exclusive, it will be 0. So that's the only difference. Because it concentrates on only either of that, only one, then it will be 1. So that's the exclusivity of the XOR gate. Right? And then we also have the NAND function. So the NAND is the inversion of the AND function. Okay, so it inverts all of the result of AND. Okay, you should got only 1 when both inputs are 1 for AND gate. But for NAND, you get 0 for both input are 1, but you get 1 for all of X and Y. Result is 0. Okay, so that's the difference between AND and NAND. So NAND is the inverter complement to the AND. Okay, and then so you look there, we have OR, XOR, and now you have NOR or NOR gates. Alright, so for NOR gates, the function is just inversion of the OR gate. Alright, so you have all of those as ones, right? All of those as 1 over here for OR gates and 0 for 0 input. Okay, but for NOR, so it is inverted, right? So you have 1 output for both X and Y are 0 and 0 for all of the results for the result of any of X and Y is 1, or also both of that are 1. Okay, so it just invert the function of OR. Alright, so we have a simple logic design to add the 2 binary digits. Okay, so if we add 2 binary digits, there are 4 possibilities. Okay, so as we learn, right? So we have carry and sum before. Okay, so whenever we add all of those, so we get the results, okay, based on the carry and sum. So when we add 1, got 1, 1, and then when we add 2, we should get 2. So mean that the carry must be 1 and the sum must be 0. Okay, as you can see that, right, the sum column, so this column, okay, let's say you have 2 inputs. Okay, the sum column is similar to the function of XOR. Okay, you look back, okay, when 1 plus 1, it should be 0, right? Okay, 1 plus 0, it should be 1. When 0 plus 1, it should be 1. And then when 0 plus 0, it should be 0. Okay, all right, so that's the function of sum. The function of sum you get by adding the XOR gate. Okay? If you want to add these 2 input, you must put the XOR gate, right? And also you must put the AND gate for the carry. Okay, then only the computer can do the calculation. Alright, so always remember, for carry we use the AND gate, for sum we use the XOR gate. Okay, so you look, is this will replicate the function of the AND gate? Yes. Okay, 0 times 0 got 0, 0 times 1 you got 0, 1 times 0 you got 0, and then 1 times 1 you got 1. Okay, all right, so this figure is showing you the, when we have the addition, so we call this as a half adder circuit. Okay, you might be familiar with half adder. So the half adder has already been taught in the electronics class as well. Okay, so the circuit diagram is like this. So you have X as the input and Y as the input as well. So the result using the XOR gate, you got the sum, and then when it's going to the input for the AND gate, so you got the carry. Okay. All right. And also, this is also a half adder, right? This is also a half adder. Why we are using this one? Okay, because this is actually much cheaper version of the half adder, because we don't need to use the XOR gate. All right, we just need to use the traditional gate, which is the inverter, AND gate, and also OR gate. Okay, but the bad thing about this is we need to have more gates. All right, we need to have more gates. Okay, but the result will be similar, okay, when you do the addition. Okay. All right. So this figure shows a block diagram of a half adder, and the two half adders can be combined to form an adder that can add 3 input digits. Okay. For example, so we take, for example, for this one, okay, we use the XOR gate. All right. So we use the XOR gate. So we add another one. Okay. So it will be double, as you can see here. All right. So we use XOR and AND, XOR and AND, and then we use another OR gate. So this becomes a full adder circuit. All right, full adder circuit. So full adder is built from two half adder. Okay, from two half adder and a OR gate. All right, and a OR gate. So this is also was learned during the electronics course. Okay. So, okay, this is the last slide for today. So we have, let's say we have, we can also have addition for more than 3 by adding, okay, by adding full adders together. So let's say this is a 3-bit adder using 3 full adders. Okay, as you can see. So we have 3 inputs. Okay, we have 3 inputs. So we have this 3-bit system. Okay, so we have 1 full adder, 2 full adder, and a second full adder, and a third full adder. So the output of this is carried to another adder, and then the output from this adder will be carried to another adder. Okay, so finally you can get the 3-bit adder. Okay, so I'll stop here for today. So we will continue with the decoder on Monday. On Tuesday. Okay. Any questions so far?
No, Doctor.
Doctor,
Yes.
can we ask for the files for the PowerPoint, the lecture slides?
You don't have the slides? I already shared.
Is it?
I already shared it on the WhatsApp group.
Oh, okay. WhatsApp group. I thought in Putra Plaza. Okay.
Yeah. I think because this is from the first chapter, so I already shared the full chapter on the slide.
Okay, Doctor. Got it.
All right. Any other question?
No.
Doctor,
Yes.
how about the subtraction example?
Okay, I need, because this slide doesn't give you the subtraction, I will add it later. Okay, I will add it later maybe we will discuss that a little bit during the next lecture. Okay,
Oh,
because I
okay.
need to insert that content from the textbook first. Okay.
Okay. Thank
Okay,
you.
maybe you can read first on the textbook, so you might find the example on the subtraction part. Okay. All right. Last before not least, so we're going to take the attendance for today's class. So please turn on your camera. Any before that, any other question?
No, Doctor.
Okay. All right. So everyone, please be ready. So I will count from 10. Okay. All right. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Cheers. Okay. Hold on. Give me a second. There's something over my keyboard. Control. Okay. Already captured the all of your faces today. All right. So enjoy the rest of the day. All right. So don't be stressful. This is just the first week of the semester. So you still have 13 week of the semesters to go. Okay. All right. So I see you next week. If you have any further question, you can just let me know. Okay. So for now, bye-bye and have a good day. Okay. Bye-bye.
Bye-bye, Doctor.
Thank you,
Bye.
Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Bye bye.
Thank you, Doctor.
Okay. Welcome.